Good morning, grade 12s. Well, I hope you guys enjoyed that Elsa video because I kind of feel like totally tired after making it, to be honest with you. But anyway, yeah, not gonna lie, it was not all terrible. I kind of had some fun with that, but yeah, the live version I had some plans for that too. But I guess we'll never know, right? So anyway, um, listen, we're going to finish off the waves unit today, and then we're not going to do a test. We're going to do quantum first, and then that'll finish off the entire course, and then we'll have a test for both. You'll see, quantum is still the same unit really. We're not changing anything. So it's really just a continuation. There's only a few lessons, so we'll get into that. You're going to like that one. It's fun. Okay, so let's finish this off. No new math today. Okay, no new like equations to look at or anything. It's just putting it all together for us. Okay, and what I wanted to do was we've established when we started this unit, we started with Huygens versus Newton. Newton had a particle model for light, okay, and Huygens had a wave model for light. Now, Newton's model was preferred for a couple of hundred years after they both died into the mid-1800s, and the reason why was, I mean, he was just more famous, really. Okay, I mean, that's not the way science is supposed to work, but Newton was considered a genius because of his work on gravity, and Huygens was relatively unknown. And so, you know, history sometimes teaches us a lesson. That's not really the way we should do things. But here's the deal. Huygens predicted that light would travel slower in glass and water and so on because waves bend towards the normal, pardon me, when they slow down. Okay, so in the late 1800s, that was confirmed that light actually travels slower in those media. So score one for Huygens, right? So that's one piece of evidence in favor of his theory, and it contradicts Newton's prediction, which he predicted it would go faster. So we have evidence falsifying Newton and confirming Huygens, right? Number two, interference. And so we spent a lot of time talking about interference in this unit. Only waves produce the phenomenon of interference. You have to have crests and troughs, or compressions and rarefactions, or whatever kind of wave you have, but you have to have a wave-like disturbance in order to have nodes and antinodes. And so as soon as they discovered that interference was a thing for light, case closed. That is proof positive that light is a wave. Okay. Now, Huygens still has one problem left. How does light make it through a vacuum? Because his whole sort of notion that there was some mysterious medium for light waves that permeated the entire universe that was eventually called ether. Well, that whole notion was not really well founded, and it turns out that evidence in the 1800s also falsified the existence of an ether medium, right? If there were an ether medium, there'd be evidence of something called an ether wind, where the speed of light would change based on the direction of travel for the Earth. And when they were able to measure the speed of light, okay, they confirmed that there could be no ether. Okay, so how does light make it through space? All waves require a medium, so how does it make it through space? Well, another theory was being developed in the mid-1800s that was making a connection between electricity and magnetism. So we saw in grade 11 physics that you can use electricity to produce magnetism, right? So when electricity passes through a wire, it produces a magnetic field. So when charges are in motion, okay, they produce, like electric fields, can induce magnetic fields, okay, for moving charges. So we saw that in the electrostatics unit this year, okay, and the electricity unit in grade 11. Now the reverse is also true, that a changing magnetic field will induce an electric field. Now these fields exist everywhere, and if I had a charged particle floating around in outer space, it would still be surrounded by an electric field, right? And if we were to accelerate through space, it would produce a magnetic field, okay? So electric fields, like gravitational fields, do go through space, okay? And they're everywhere. So these fields are everywhere, And so it was in the mid-1800s that they discovered by accident, by doing electricity with electricity alternating current in a wire, that another wire sitting on the table nearby would have little sparks whenever the little sparks in it. It was not connected to a power source, but when this experiment was running, it would induce a signal, okay, in another wire sitting on the table. And what they had discovered inadvertently were radio waves, which is a form of light with a very long wavelength that we can't see, okay? But think of how important they are in our society today. Like your cell phone signal is a radio signal, right? Wi-Fi is a radio signal. Radio technology is crucial, okay, when you think about just Wi-Fi, how important that is, right, in our world today. Like I'm using it right now, okay, to connect to the internet, as many of us are probably, right, sitting at home. So Wi-Fi signals are radio signals. They discovered that, guys, 150 years ago, right, in the mid 1800s, and they discovered this connection between electricity and magnetism. And it turns out that that is the solution to Huygens' problem of how light gets through space. Okay, what happens is the medium for light is really an electric field. Okay, so charged particles are surrounded by electric fields. So here's a wire. Okay, now in this little thing here, the wire can carry current. Now current is a set, series of moving charged particles like electrons. Now when the current accelerates up and down this wire, the electric field around the wire will change. Okay, now that is a disturbance in the electric field that will propagate out away from the wire, okay, at the speed of light, at 3 × 10⁸ meters per second in a vacuum. And this changing electric field will also induce a magnetic field, okay, and so this whole thing propagates out into space in the form of an electromagnetic disturbance. And that's how light travels through outer space without any other medium. It's a disturbance not in a medium like a particle medium like water for water waves or air for sound waves or anything like that, but it's a disturbance in an electric field that propagates along electric field lines. Okay, and that's what light is. Okay, it's an electromagnetic disturbance. Now if I run the simulation, you can see what happens when current flows through the wire. Okay. So when current is flowing through the wire, the current alternates like, sorry, I got distracted. Okay, so when current flows through the wire, what's happening is the field around the wire changes. And you can see these green and red waves propagating out into space. The arrows indicate changes that are taking place in the field. But that wave, okay, is a field disturbance. Okay, now the Van der Graaf machine at school that makes your hair stand up, when that thing discharges, you'll hear little pops in my speakers, okay? The speakers are like, connected to a source that has an antenna on it. Okay, so what happens is that this disturbance, if it intersects the antenna on the speaker, what it can do, like that's attached to the speaker anyway, it will induce a sound in the speaker. And what we've shown then is that the Van der Graaf is producing these radio waves. Okay, so that's what light is. So now we've got it all put together, right? We've got this coherent theory that shows that light is a wave, and it explains, it's so experimentally successful, guys. Like this theory, electromagnetic wave theory, is probably one of the most successful theories ever put on paper. I mean, like, how do we measure the success of the theory? Well, it makes predictions that you can test, right? So basically, somebody predicted that you could make a radio and transmit a signal across the ocean, whatever, and they invented that in the late 1800s, and it worked. Okay, and fast forward all the way to today and think about everything I said about radio waves, Wi-Fi, and so on, microwaves, and et cetera, et cetera, et cetera. The electromagnetic wave theory changed the world, okay? Even generators and motors and everything else, like electric motors, electric generators. Imagine the world without electricity, right? It was the electromagnetic wave theory that actually allowed us to build generators, motors, and everything that we learned about last year. okay, plus your cell phone technology, plus radios, plus everything else, all successfully predicted and then engineers took that theory and look at all these applications that they came up with. So it's this incredibly important moment in our history, you know, for better or for worse for the planet, but it really started the modern age, right? Where there's this explosion in technology. Okay, so anyway, Huygens was right. He wasn't right about the ether, but he was right about everything else. That light is a wave. Okay, it's this transverse wave we saw with polarization. Okay, and it produces interference and so on. And the electromagnetic wave theory explains how it gets through space. Okay, so you put it all together, we got this amazing sort of complete picture of what light is, how it propagates, right? How it produces interference, how polarization works, everything else, even 3D glasses that we use in a 3D movie. Okay, you can thank these guys in the late 1800s for that. You know, coming like this sort of understanding of the connection between electricity and magnetism, electromagnetic waves, and light. Okay. All right, I'm going to stop this video here, and I'm going to get to the notes. Like I said, it's just more theory today, no equation or anything like that, no problems to solve, and we'll get to that in a moment.